Okay, we are now going to figure out the delta H dissolution for urea. Involves using a coffee cup. Our goal is to get the change in temperature. We know the change in temperature, we can plug that into the MCAT formula and figure out the energy that is in the chemical reaction that goes into water. Okay, and then we'll know the delta H. It's the opposite sign of water. Now, in order of the temperature change, okay, we've got an initial of 19.8 degrees Celsius. I am using 45 grams of water. Less is better though, so this is okay. And I've got 3.5 grams of urea, nice white powder on the side. And somebody say, ooh, it's urea, gross, man. That's urine, that's a little bit gross, but this is urea, and it actually does not smell too bad, or has any smell at all. So now we're just going to dump this in here and measure the temperature change on our thermometer right here. Okay, 19.8. Here we go. Just take our solid, dump it in, swirl, 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 mix it all around. Swirl, swirl, swirl until our temp is found, and it's rapidly going down. We're down to 16.1, 16, 15.9. Lots of stirring, lots of swirling. Okay, this one's only going down about 15.9 or so degrees. Got a little colder last time, but it's pretty cool. All right, so 15.9, and I check in there, and yep, it's all dissolved. And 15.9 was the lowest temperature that I had gotten to. So now we can use 15.9 as our final temperature. Okay, and we can now plug that in to our MCAT formula to figure out delta T once again. And we know the mass will be just the mass of water. That's okay. And once we figure out the Q for water, we'll take the opposite sign. And remember the units that it's all in. And we'll need to get it per mole of urea. Okay, don't forget the per mole calculation. Okay, we're going to calculate now, do the calculation for the enthalpy of dissolution. From the experiment, we learned there was 45 grams of water, 3.5 grams of urea, and the temperature change was 3.9 degrees, or negative 3.9 degrees because it got cooler. We can calculate the Q, the energy that went into the water, by taking the mass of water times the specific heat of water, and the delta T for the temperature change of the reaction. So let's plug it all in. And you can see the grams and the Celsius cancel out, and we have nothing but joules. Negative 734 joules for this particular experiment. But if we recall, the energy that's going into water is the opposite of what came out of the reaction. So we had to take the negative of it. And that's how much energy came out of 3.5 grams of urea. We need it per mole, so we convert the grams of urea to mole, dividing by the molecular weight. And now taking the energy, which now is positive because it's endothermic, the temperature went down, and we essentially divide it by the number of moles in the experiment, getting 12,600 joules. And when we convert that to kilojoules, we can see it's roughly around 13, give or take. Two significant digits because of the delta T and some of the mass readings that are in the experiment. So that is where our sig digs come from, and that is the enthalpy of dissolution.